we are going to start module 2 of chapter 3. In this module, we are interested to obtain Lagrange's equation of motion for a non-holonomic dynamical system. If a dynamical system contains non-holonomic constants, then without violating the constant relation, it is not possible to give the independent or arbitrary variations to the generalized coordinates. In such cases, the equations expressing the constant relations are of little help to eliminate the dependent coordinates. In such cases, this leads us to obtain Lagrange's equation of motion for non-holonomic dynamical system. In this module, we shall discuss Lagrange's equation of motion for a non-holonomic dynamical system. First of all, we shall obtain Lagrange's equations of motion in a non-holonomic dynamical system. Later on, we shall derive Lagrange's equation in a dynamical system which is moving in a velocity dependent potential field. In previous module, that is module 1 of chapter 3, we have obtained Lagrange's equation of motion in a holonomic dynamical system having k bilateral constants. In this module, we shall discuss Lagrange's equation of motion for a non-holonomic dynamical system. First of all, let us define non-holonomic dynamical system. Let me first define non-holonomic constants. We have already defined it in chapter 2. Let us recall it again. In case of non-holonomic constants, it is not possible to give arbitrary and independent variations to the generalized coordinates without violating the constant relations. The dynamical system containing non-holonomic constants are known as non-holonomic dynamical system. Basically, non-holonomic constants are non-integrable relations, and a non-holonomic dynamical system contains such type of constraints. Let us derive Lagrange's equation of motion for such a dynamical system. In such system, the changes delta q1, delta q2 up to delta qk are connected by k non-integrable relations. Please note that we are considering virtual changes, that is why Kronecker delta symbol has been used. The non-integrable relations are given by aj into delta t plus summation over e aje into delta qe equal to 0. This is valid for j equal to 1, 2 up to k. K must be less than small n. Here n is the number of degrees of freedom and k is the number of constant relations. So k must be less than small n. Aj are functions of the generalized coordinates. Let us consider the virtual change in time t. As we are considering virtual change, so the time t is fixed, and this gives summation over e aje into delta qe equal to 0. We have mentioned that we are considering virtual change. Virtual change means time t is fixed, so delta t vanishes. From this equation we get this relation. This is valid for j equal to 1, 2 and so on k. K must be less than n. The changes delta q1, delta q2 up to delta qk are not independent, as they are connected by k number of non-integrable relations. Multiplying the previous equation by the parameter lambda j and summing over j, we get this result, where lambda j, j equal to 1, 2 and so on k are k number of arbitrary parameters. We can write this equation in this way. Just we have interchanged the summation and get it. If we add this equation with the Lagrange's equation of motion for n degrees of freedom, which is given by this equation, we get this equation, that is summation over E capital Q suffix E minus ddt of first order partial derivative of capital T with respect to QE dot minus first order partial derivative of capital T with respect to QE plus summation over j lambda j into AJE into delta QE equal to 0. Capital QE is the generalized force associated with the generalized coordinate QE. QE dot is the generalized velocity. T is the time. Lambda j are the parameters. We have already mentioned it. Let us choose the parameters lambda 1, lambda 2 up to lambda k, so that the coefficients of the changes delta q1, delta q2 up to delta qk vanish separately. Then we have capital QE minus ddt of del del QE dot of capital T minus del del QE of capital T plus summation over j lambda j into AJE equal to 0. This is valid for E equal to 1, 2 up to n. N gives the number of degrees of freedom of the dynamical system. Shifting the term within the second bracket in the right hand side, we can write this equation in this form. These are the Lagrange's equations of motion valid for a non-holonomic dynamical system. To solve these equations, we have to supply the constraint relations, which have been given in the modified form here. QE dot means ddt of QE. This is valid for j equal to 1, 2 up to k, since there are k number of constraint relations. If the generalized force is given by this relation, where capital V is the potential function and the Lagrangian is the difference between the kinetic energy and potential energy of the system, then the previous equation can be written like this. Here QE is the generalized coordinate, QE dot is the generalized velocity, dot means time derivative of QE, lambda j are the parameters, L is the Lagrangian of the system t is the time. Let us obtain the physical significance of the parameters lambdas. Suppose we have removed the constraints of the system. To keep the system unchanged, we have to apply external forces. Let the external forces be capital Q, E dash. As a result, the system will be unchanged. Under the influence of the forces QE dash, the equations of motion now take the form ddt of del L del QE dot minus del L del QE equal to capital QE dash. This equation is valid for E equal to 1, 2 and so on n. N is the number of degrees of freedom. This is the generalized force QE dash, L is the Lagrangian of the system, small QE is the generalized coordinate, QE dot is the generalized velocity, t is the time. This must be identical with the previous equation, which is given by this one. The left hand side of both the equations are same, they differ only in the right hand side. So, QE dash can be identified with summation over j lambda j into AJE. This is the physical significance of the generalized forces QE dash. A general equation of motion known as Lagrange's equation of motion of second kind for a non-holonomic dynamical system has been derived. In the derivation of such equation, the knowledge of forces of constants has not been used. Only we have used the knowledge of work, energy and also the virtual work principle has been used. Now let us derive Lagrange's equations of motion in a system moving in a velocity dependent potential field. So far we have obtained Lagrange's equations of motion in holonomic dynamical system as well as non-holonomic dynamical system. In both cases, the velocity potential depends on the generalized coordinate only. Here we have to consider the motion where the system is moving in a velocity dependent potential field. In Newtonian mechanics, it is well known that the potential is a function of coordinates only. But we have already known that the Lagrangian can be written as the difference between the kinetic energy and potential energy. So, potential is a part of the Lagrangian. As Lagrangian depends on generalized velocity, so the potential may depend on velocities. That is why we have to consider the Lagrange's equation of motion in a velocity independent potential field as well as velocity dependent potential field. We have already obtained Lagrange's equations of motion in a velocity independent potential field, which are given by this one. T is the kinetic energy, capital QE is the generalized force, where capital QE is equal to minus del del QE of capital V. Here V depends on generalized coordinate only, not on generalized velocity. Let capital QE be obtained from a potential function capital U, which is a function of generalized coordinate generalized velocity and time t, so that capital QE can be expressed in this way. If we substitute this here, we get the Lagrange's equation of motion in this form. This equation can be written in this way. We have just shifted the right hand terms on the right hand side into the left hand side. This term and this term has been written here, and this term and this term has been written here. If we set L equal to T minus U, that is L is the Lagrangian of the system, which is the difference between kinetic energy and potential function, then the above equation can be written like this. This equation is valid for E equal to 1, 2 up to small n. These are the Lagrange's equations of motion valid in a velocity dependent potential field. U is the generalized potential, as it depends on generalized coordinate, generalized velocity, so the term generalized is used here. One can remark that Lagrangian is a scalar point function of the generalized coordinates, generalized velocities as well as time. Moreover, Lagrangian is described in a n-dimensional space. It cannot be uniquely specified as it depends on generalized coordinate qk, generalized velocity qk dot and time t. Moreover, Lagrangian has the dimension of energy since it is expressed as the difference of kinetic and potential energy of that dynamical system. It will satisfy Lagrange's equation of motion if ddt of del del qi dot operated on L dash minus del del qi operated on L dash equal to 0. That is, if this equation holds. Here we have just substituted the expression for L dash, that is L dash equal to L plus ddt of capital F, and get this equation. The previous equation can be arranged in this way. If this holds, then we can say that L dash satisfies Lagrange's equations of motion. Now let us check it. ddt of capital F is given by del del t of capital F plus summation over I del del qi of capital F into qi dot. Here we have used the chain rule of differentiation, since capital F depends on qi as well as time t and qi depends on time t. So we get this result. If we differentiate this equation with respect to qi dot partially, we get this result. This is independent of qi dot. Qi dot is present here, so we get this term. Thus, ddt of del del qi dot of df dt equal to ddt of, if we use the previous result here, we get del del Qi of capital F. Interchanging the ddt operation and del del Qi operation, we get this result. Shifting the right hand side into the left hand side, we get this equation. If we use this in this equation, we get this portion vanishes. So, we only have ddt of del L del Qi dot minus del L del Qi equal to 0. As L satisfies Lagrange's equation of motion, then we have this. So, one can comment that L dash also satisfies Lagrange's equation of motion. Here the function capital F is known as gauge function of the Lagrangian. F depends on generalized coordinate Qi and time t. In this module, we have discussed a general equation of motion known as Lagrange's equation of motion of second kind. This has been extended to include the non-holonomic constants. Moreover, Lagrange's equation of motion has been derived for velocity dependent potential field.